I welcome to all the students to the college Y&M AKI Pune College of Arts, Science and Commerce College Camp Pune 1. I teach statistics, paper 1, discrete probability distribution and time series. I had given you one multiple choice test, that is quiz, and I got the responses also. 22 students appeared in the quiz. After this class, I will release the score, then you will get the score also. Last, we finished negative binomial distribution, and on the basis of that chapter, I took a test. The score obtained by you will be considered for your internal assessment. Today we are going to see the next chapter known as multinomial distribution.
Sir,
Yes,
the numerical problems.
I took last time numerical problems. I think you were absent. Last lecture I took numericals and I have discussed multinomial distribution little bit. But I will repeat again entire multinomial distribution. If you have any difficulty, you can see the notes, as well as I uploaded the corresponding video on a Google class. So you can go to Google class and again try to listen, and if you have doubt, you can ask me. Okay?
Yes, sir.
Let me proceed now for chapter number 2, multinomial distribution. It is extension of binomial distribution. The difference between binomial and multinomial: in case of binomial, we study the random experiment in which every trial had two possible outcomes. We classify the outcome as failure and the other outcome as a success. So in real life, there are many problems, many situations where random experiment provides two possible results. I told many times, tossing of a coin is a standard example for binomial experiment. Result of examination, either pass or fail, the quality of product, good or bad, and so on. So there are many examples where we get two possible outcomes in a trial. So in such cases, we use binomial distribution that you people already studied at your first year level. Now, today we are speaking about multinomial distribution. Now, the experiment, when I perform, it may have more than two outcomes. So in this case, we go for multinomial distribution. Very simple example for multinomial distribution is throwing of a dice. We know dice has 6 possible outcomes. Dice is nothing but a cube, and cube has 6 different faces. So in this experiment, I will not have two results. I will have more than two results. So whenever random experiment has more than two possible outcomes in every trial, then corresponding experiment can be analyzed by using a multinomial distribution. Firstly, we'll try to define the multinomial distribution and then we'll go ahead. A discrete k-dimensional random variable x as a vector. So we write a vector as x bar, bar is written at the bottom. I told last time it is a convention for us. Mathematical way of denoting vector is bar indicate on the top. But in statistics, if I put bar on the top, it has another meaning, and that is the mean, average. So to overcome this difficulty, we put bar in the bottom. So I read x vector equal to bracket x1, x2, dash dash xk. That means x vector has k component, k elements. So there are k variables, I can say. K dimensional means there are k variables. Said to follow multinomial distribution if its joint probability distribution. Excuse me. Hello. अजय, कौन बात कर रहे हैं? अभी मैंने लिंक दिया है ना, वो लिंक से ज्वाइन हो जाओ ना आप. नहीं नहीं, वो जो ग्रुप के ऊपर लिंक है ना, हाँ वो लिंक से ज्वाइन होना है. ओके. ऋतुजा ज्वाइन हो गए आप?
हाँ सर.
हेलो
यस सर.
ऋतुजा.
हाँ यस.
ओके. So I was speaking about definition of multinomial distribution. X vector having k components said to follow multinomial distribution if its joint, it is not Z, it is J. Joint probability distribution is given by. So how to write? It is a probability, capital X1 taking value small x1, capital X2 as a random variable having many values. At particular, it takes value small x2 and like this up to xk. So this is a multivariate function. What I taught about NBD, it is a univariate function, only one variable. But for multinomial, we have k variables under study. So the function is defined as n factorial. So n stands for number of repetition of the experiment. N factorial total divide x1 factorial, x2 factorial, xk factorial. P1 small p1 to the power x1 multiply small p to the power x2 small p3 to the power x3 dash pk to the power xk. So this is your entire PMF, which I am highlighting by this yellow color. So whenever you want to define multinomial distribution, you should remember this formula entirely. Now in this case, what is your variable takes values xi, maybe 1, maybe 2, maybe k. So all xi begin from 0, 1, 2, and it end with some specified number, that is n minus summation xr, r from 1 to I minus 1. So this is the range of ith variable under multinomial distribution. In addition to this, we put a condition on the variable x1 plus x2 dash dash xk. The total of these all k variables should be n. In addition to this, total of probabilities P1 for x1, that means chance of taking value x1 by capital X1, P1, P2, Pk, the total probability should be 1. So whenever you want to define multinomial distribution, you have to write this entire thing in exam. There should not be mistake in this writing. Then you will get complete marks. If you write only this much, you will not get full credit. So if you want full credit for your definition, after writing a formula, you have to explain each and every notation used in the formula. So after defining this, I have a notation to indicate multinomial distribution. So I write x vector, I can say directly follows multinomial distribution in bracket. So in bracket what I write, it is called as a parameter of that distribution. Just like in NBD, we write a notation x follows NB in bracket k comma p. So k comma p are known as a parameter for NBD. Similarly, for multinomial distribution with k variables, I required n as a repetition of experiment, and these are the probabilities for each of the variables. So this is the notation for your multinomial distribution. Now we go ahead, remark on this multinomial distribution. Remark number 1, small n, P1, P2, Pk be the parameters of multinomial distribution. Remark number 2, for multinomial distribution, we have k variables with linear constraint. The spelling is wrong. It is constraint or condition. What is the constraint? Just now I told in case of definition. Addition of all these k values taken by k variables should be small n. Now, what is the impact of this constraint? Due to this constraint, we can write any one out of k in terms of remaining k minus 1. So, in a true sense, we are not studying k variable, we study only k minus 1. Because out of k, any one can be expressed in terms of remaining k minus 1. So, if you have a knowledge of k minus 1, you can decide the remaining one variable easily. For example, if I study three variables, x1, x2, x3, and I put a condition, x1 plus x2 plus x3 equal to 10. That means small n is a 10. And I provide you two numbers, x1 taking value, suppose 3, and x2 taking value, suppose 5. So, does it necessary to tell about what is x3 value? Not, because linear constraint says x1 plus x2 plus x3 is 10. So, naturally, x3 will be 10 minus x1 minus x2. So, answer will become 2. That means, for studying a multinomial distribution, we don't require k variable exactly. If you have knowledge of k minus 1, you can study k variables. So, in other words, there are k minus 1 independent variables and one variable is depend on this k minus 1. Just like I told, x1 plus x2 plus x3 is 10. So, I can write any one in terms of other. So, out of three variables, one variable depend on other two and the two are independent. So, in general, if you study k variables, number of independent variables are k minus 1 and 1 is a dependent variable. So, in multinomial distribution, the particular variable follows binomial distribution with parameter n comma pi. Pi is missing there. That means this third remark is very important. Out of k variables, if I decide to study any one, so one variable particularly follows binomial, and you know binomial distribution from your first year. Let us proceed ahead. Real life situations of multinomial distribution. We use multinomial distribution for random variable having more than two mutually exclusive, that means disjoint outcomes. So, any experiment which has more than two mutually exclusive outcomes, in that situation, you can go with multinomial distribution. For example, you are taking a survey in a blood bank. So, when you go for collecting the blood through certain blood bank, then in the population, in the donor, for every donor, there is 4 possibilities. It may be O, it may be A, it may be B, it may be AB. So, every individual has 4 different possibilities. And that's why This type of experiment can be analyzed with the help of multinomial distribution. Second real life situation is how many dots on upward face of a dice. You have a dice, you throw it, it will be rest on one face on the top, and you count how many dots are there. So you will have a possibility maybe having 1 dot, 2 dot, 3, 4, 5 and 6. So there are 6 possible outcomes in every trial, and that's why this is also experiment which can be analyzed through multinomial distribution. Third example of real life where you can think to apply multinomial distribution, that is grade obtained in exam by a particular student. Suppose I specify the grade 1, 2, 3, 4 like this. So every student has 4 possibility of grading. That means I divide my performance of the student on a 4 scale point. So student may get first grade, second grade, third grade and fourth grade. So these are the examples where you can apply multinomial distribution. Now the next topic is to develop MGF, moment generating function of multinomial distribution. Because to study any distribution, properties of distribution, we should know the corresponding moments. And for that purpose, we develop the MGF. See how to develop MGF of multinomial. Let x vector equal to bracket x1, x2, xk, k-dimensional vector follows multinomial distribution bracket small n, comma p1, p2 dash dash pk. Then its MGF is obtained as below. We write MGF by capital M as a subscript. If there is one variable, we write x. If there is more than one variable, we write x1, comma x2. Now in this case, there are k variables. In bracket, x1 is evaluated at a point t1, MGF of x2 evaluated with t2 like this tk. This equal to expected value bracket e to the power t1 x1 plus t2 x2 plus dash dash tk xk. If you recall your previous chapter, mxt is written as expected value e to the power tx. That is for one variable. Now if there is more than one variable, you go by such definition. I repeat, expected value of bracket small e to the power t1 x1 plus t2 x2 plus dash dash tk xk. This is a plus sign there. How to evaluate this? This equal to, now if there is an expectation of one variable, capital E replaced by one summation. Now this is the expectation for k variable, so E will be replaced by k summations. So summation with x1, sum with x2, dash dash sum with xk. And I told you the way of writing expectation. E replaced by summation. What is inside expectation? Write as it is. multiply corresponding function. So this is my function of multinomial distribution. Let us proceed ahead. Summation continue. I split this. It is a power plus. So you know school mathematics. A raised to m plus n will be written as a raised to m multiply a raised to n. So this can be splitted separately like this. Function continue as it is. Now this t1 power x1, e to the power t1 and this whole power x1, these two terms can be combined. These two terms can be combined. These two terms can be combined. So you get a next term, summation as it is. T1 multiply this with common power x1. T2 multiply this with common power x2. Tk multiply this with common power xk. This factorial as it is. Now I use the concept of binomial theorem. So this is nothing but a binomial theorem. So answer of this is nothing but this entire thing by using a result of binomial. This total term is bracket t1 multiply e to the power t1 plus t2 multiply e to the power t2 plus dash dash, here plus sign should be there, tk e to the power tk whole bracket raised to n. Now explanation of binomial theorem, how I write this. So this is the final answer for MGF of multinomial distribution to be remembered nicely, because all coming results will be based on this formula. So this expression is very important for making further derivations. Let us see the derivation for getting a mean of ith random variable in mean deviation multinomial distribution using MGF. That means we use this expression. We use this expression to get a mean, to get a variance, to get a covariance, this correlation, this everything we develop from this function. Mean of ith random variable is equal to expected value of xi. This is by first definition. Through MGF, we differentiate MGF for ith random variable ti, mx vector, t vector. So writing this big expression, you can make it short, mx vector bracket t vector. That means x vector has a k element, t vector has a k element. After making a differentiation, we replace all the value of t vector as 0. And then we get answer for mean by using MGF, not by expected value. So what is the next step? D by dti, this is the DABA. DABA means partial differentiation, D means total differentiation. It is DABA by DABA ti. This is the MGF, what we derived just now. You can see on the screen, this is the MGF. So I differentiate this function for particular variable I. and then I replace t equal to 0. Recall your differentiation knowledge from mathematics. This is a function with power n. So whenever I differentiate such quantity, what is the rule of differentiation? Power get multiplied. Function remain as it is. Power reduced by 1. Then multiply the differentiation of function inside the bracket. Now you differentiating ith term. It is a partial differentiation, so only I is a variable, the rest are constant. So differentiation of this becomes 0. Differentiation of this becomes 0. Differentiation of last becomes 0. At the middle place, there is some place I. So differentiation of this I write here. Pi is a constant multiplied as it is. Differentiation of exponential as it is. Multiply differentiation of power, that is Ti with Ti, become 1. So that is not written. Now this is the end of differentiation of this quantity with respect to Ti. Now I replace everywhere T as 0. That means T1 becomes 0, T2 becomes 0, Ti becomes 0, Tk becomes 0. Anything power 0 is 1. So what is this bracket? This bracket is nothing but P1 plus P2 plus dash dash Pi plus dash dash plus Pk. So you get next term as n multiply P1 plus P2 dash dash Pi plus dash dash Pk complete power n minus 1 multiply just Pi, because here also t equal to 0, so this get cancelled. So multiply by Pi. Now, therefore, expected value for ith variable answer is n multiply Pi. Now, where is this bracket gone? This bracket is 1, because in the definition I told sum of all probability is equal to 1, and 1 to the power anything is 1, and that's why this bracket is not written here. What is I? It may be 1, it may be 2, it may be any number. Now you can correlate this answer with your first year knowledge. Under remark, I told any particular variable of multinomial is a binomial, and we know mean of binomial is NP. So for ith variable, it is NPI. I think everybody understands this. Biologically, if particular variable I want to study, it is a binomial, and mean of particular variable of multinomial is n into Pi. Let us proceed ahead how to get answer of variance. Variance of ith multinomial random variable. Let x vector follows multinomial distribution with parameters small n, comma P1, P2 dash dash Pk. Then variance of ith random variable is obtained as below. This is the definition: variance of x, any random variable x. It is simplified definition: expected value of xi square minus square of expectation. So I replace x as a xi for ith variable under multinomial. That means to get answer of variance, you need two calculations. Expectation of square of x and expectation of x, which we got just now. So E of xi is npi. The second term is known to us. E of xi is n times pi. Let us see how to develop E of xi square by MGF approach. So it is d square dti square mx vector t vector. Once you finish two time differentiation, you replace t vector as a 0, just like what we did for mean. So I write d square by dti square as d by dti curly bracket d by dti. Here d square means not a square, it is two time differentiation. So this is one, this is another time. Inside MGF of multinomial, which we got. Now I write a differentiation of this, what we did for mean. Power become multiplied, complete bracket as it is, power reduced by 1 into differentiation of this bracket for I. So it is pi e to the power ti. Now at this stage you can see there are two functions in terms of ti. This is the bracket having ti and there is a ti in outside also. So I have to use product rule of differentiation. So this n, this pi is a constant because differentiation for ti. So I put n, I put pi outside. D by dti of this bracket multiply this quantity. So I say this as a v and this entire bracket as a u. And then I have result differentiation of product, keep one as it is and differentiate other, plus keep other as it is and differentiation of first. So by using this result of differentiation, we get answer like this: E of xi square equal n times pi, which is outside the term, complete bracket as it is, power n minus 1, so first term as it is, and differentiation of exponential remain as it is, plus second term as it is into differentiation of first term. So this n minus 1 become multiplied, this complete bracket will be as it is, power become n minus 2 into differentiation of this bracket for ti, so it is pi e to the power ti. That is not come in the scan copy, but you can realize it. So n times pi. Now when I replace t equal to 0, this becomes p1 plus dot dot plus pk, n minus 1 e to the power 0 is 1, so this cancel, plus e to the power 0 is 1 cancel, n minus 1, this is p1 plus p2 n to the power minus 2 into pi e to the power 0 is 1. So I get simplified expression, sum of probability is 1, so that bracket cancel. So you get this as 1, 1 to the power anything is 1, so this replace as 1. So npi bracket 1 plus n minus 1, and this bracket is 1, so it is cancelled, and here it is pi. So n minus 1 multiply pi. That is your next expression. N time pi, 1 plus n minus 1 pi. Let us multiply n pi inside. So n pi plus n into n minus 1 pi multiply pi become pi square. So I got expected value of xi square. Now easily I can go for variance of xi. So expected value of xi square minus square of expectation. It is just repetition from your first year practice. E of xi square, which is here. Replace this in place of ei xi square. N time pi plus n into n minus 1 pi square. E of xi you got before as E of xi is n pi. So put it here and make a square. So it is n square pi square, n multiply n square pi square, n multiply minus 1 pi square. This is plus and this is minus, get cancelled. Now from here and here, npi is common. So npi, this will be 1 minus pi. And what is 1 minus p? It is q. So 1 minus pi becomes qi. Finally, variance of xi, n pi qi. I take value 1 to k, which coincide the knowledge of binomial. If x is a binomial random variable, mean is npi and variance is npq. For particular variable I, it will be npiqi. So for particular variable of multinomial, the result of binomial distribution hold. It's true. And therefore, you can remember mean of ith random variable in multinomial distribution is npi. And variance of ith random variable in multinomial distribution is npiqi. Now I put one theoretical question on today's topic. The question is like this: define multinomial distribution, obtain its mean and variance of ith random variable in multinomial distribution. So what I took today, that you have to explain. In this case, you can use directly MGF of multinomial. Not necessary to find MGF and then proceed ahead. But you have another question where you have to develop the MGF. And that question is, obtain MGF of multinomial distribution. Hence, that means after having MGF, find mean and variance of ith random variable. So these are the two questions can be asked on today's topic.